Okay, thank you. Should I start? Yes. So yeah, thank you for the invitation. It's very interesting to be talking about supersymmetry to this audience, and so I will try to make it interesting and accessible to everyone. Well, I will probably fail partly, but you please stop me if you have any questions, and then maybe we can discuss a bit more at the end. But if you have any question during the talk or anything is not clear, please stop me and ask. So the plan of this next hour is as follows. It's slightly different as what I advertised in the abstract in terms of the order, at least. I will first try to give what is essentially a history lesson of physics and particle physics in particular, and how supersymmetry fits into it, and how it appeared, and what it is in particle physics. And then, because supersymmetry is really a very like almost elementary notion that you could call almost pure mathematics, I will give, in fact, an example of supersymmetry in a toy model of physics, which is essentially elementary calculus, and there I will have some part which is a bit more technical, but really that any first year in physics or math should be able to follow. And then after that, I will go back a bit to a more discursive discussion of application then of supersymmetry, as we will see, not only in kind of motivated by particle physics, but where supersymmetry then really has an import into pure mathematics. So let me go back to the very beginning with the notion of atom. And as we know, atoms as an idea, as a really philosophical idea for the ancient Greeks, has been there since more than 2,000 years ago. And it was just, well, I guess, again, a philosophical idea, but nonetheless a very powerful one that we've come back to again and again. So maybe the atomic principle was most beautifully expressed in that very long poem by the Roman poet Lucretius in the 1st century BC, where he was explaining then there must be some true beginning of things, some things that no force can quench, for they by their solid body prevail in the end. So that the atoms will be the things, I quote, which exist with solid and everlasting body, which we show to be the seeds of things and their first beginning, out of which the whole sum of things no stands created. And well, in modern physics, we call atoms something slightly different than what they had in mind, but they were not that far off. And in fact, some of the arguments that they had for atoms back then are actually very scientific in their, even though they didn't have the labs we have and so on, but some of the ideas were pretty much correct. A lot of the details, of course, were completely wrong. There we go.
Just real quick, are you seeing your slides right now? Because we're still seeing the first slide.
Oh, sorry, this one? It should be sharing.
Maybe try restarting the sharing, because we're still seeing the first slide.
Oh, that's bad. Okay, let me just, maybe I'll just share. Well, let me try again.
Yeah, that's it.
That's work?
Yeah.
Oh, sorry. So yeah, tell me if that happens again. Sometimes I see that Zoom has this kind of bug on my computer. So yeah, so I was showing this. So you didn't see this?
No, but I assumed that we probably should. Yeah.
I'm so sorry.
No worries.
So anyway, I was quoting Lucretius then about the atoms. And well, of course, they thought that atoms was those little things that are unbreakable. That's the etymology in Greek. And then we called atoms those things that we're building, that we discovered in the 19th century. And then we realized, both tragically and excitingly, that in the 1940s, that we could actually break the atoms. Now, Richard Feynman in 1961, in his at the beginning of his lectures on physics, asked this rhetorical question: if there was some cataclysm and all scientific knowledge vanished, how would you carry on in one sentence the most important scientific achievement or understanding for the next generation? And he said, let me quote, "I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are little distance apart, but repelling upon when being squeezed into one another." In that one sentence, we will see there is an enormous amount of information about the world if just a little imagination and thinking is applied. And so we see in this quote, what I want to get at is the raw power of ideas. Of course, we use in science, and we should be aware that scientific experiments are the ultimate arbiter of the truth or the validity of an hypothesis. But nonetheless, if you take ideas and using mathematics and so on, if you take ideas and logic seriously, you can often get a very long way towards the truth, whatever that might be. In fact, as I said before, even in Lucretius, there were some correct arguments about atoms, or we would say today molecules, when they describe the thing that we now call Brownian motion. When you have a little like speck of dust in water and you see that it moves randomly in water, you can explain that by the fact that there are molecules that make the water. Okay, so of course, what makes our scientific theories much stronger in some sense than ancient philosophy is that we can test them very precisely. And this is because we rely not on hexameter verses like Lucretius to describe these theories, but we rely on the mathematics. And so this talk is really about mathematical physics, and in a very broad sense, all of physics today, at least since Galileo and Newton, is mathematical physics. So mathematics by itself would be the study of ideal forms, but physics, by contrast, is a study of nature, physis in Greek, what I will call just reality, or the world as we observe it. And we observe the world more and more precisely with more ingenious tricks and methods, labs, and so on. So Galileo summarizes this opinion of many later generations of scientists when he wrote in the 17th century that philosophy is written in this great book, which stands continuously open to our gaze, the universe, but it cannot be understood unless one first learns the language in which the book of nature is written, and this language, he said, is mathematics. And it's interesting to insist on the fact that until relatively recently, physics and mathematics were not really distinct disciplines. I mean, some people were maybe more mathematicians and physicists, but many people were like, we would consider scientists today, were called like natural philosophers, and they were often as much mathematicians as physicists, and they would develop whatever mathematics they needed to understand the world and so on. For instance, Newton himself invented calculus in parallel with Leibniz, who invented it independently. Nonetheless, the distinction between physics and mathematics, in the sense of having some kind of pure ideas and something which is the world we live in, is very ancient. And in modern notation, maybe tongue-in-cheek, we could say that physics is then like a subset of mathematics. If mathematics is really the language of the world, well, there is a unique world, and we need to actually read this book now. And so we first learn the language, and then you try to see what the world is actually look like in this language. And physics and mathematics have always been intertwined, with important ideas flowing in both directions. As I just mentioned, precisely to understand mechanics, the motion of planets, and so on and so forth, Newton had to invent the proper tools, and those are calculus that we now teach in high school and in first year at university. Similarly, the whole field of statistics and probability theory was developed in good part because of the need of physics to understand thermodynamics and statistical mechanics. There are also the huge realm of abstract algebra, a huge part of mathematics, which in good part was invented by mathematicians over many centuries for their own reason, not directly connected to physics, but a lot of it then become much more useful in 20th century physics, starting with quantum mechanics, which in some sense is just linear algebra. And more recently, there are a lot of like more advanced physics, like string theory and some of the things I will talk about, which rely on more, you might say, highbrow or advanced mathematics, which is very much studied to this day by the mathematicians here, for instance, at the Math Institute, like algebraic geometry. Now let me go back for a second to this notion of the atom, this unbreakable unit of things, of stuff, of matter, this building block. So related to this crazy idea, this crazy hypothesis that we know to be true in some sense, there is the idea that the world, there was the idea back in the days that the world is empty. There is such a thing as a vacuum, which is not obvious at all if you really think about, the world as we experience it. Of course, everything seems very solid. There is air or water or everything around us, but they have this idea that if you think of this atom as some kind of small marble, that it has to move around in vacuum. And of course, this idea was taken on again much more powerfully by Galileo and Newton to understand matter and how it's acted on by force. So modern physics really starts with Galileo and then Newton when they describe precisely mathematically how particles are acted on by force with this kind of differential equation that you're all familiar with. Then more recently, we had a kind of slight upgrade. I mean, rather conceptually, it looks a bit daunting, but in the end, it's only a slight upgrade on this picture of the world, which is quantum mechanics, where the kind of notion of what is matter is slightly more subtle, but still there is such a thing as elementary particles. And those elementary particles that we discovered, like the electrons, then the proton and neutrons, which are themselves actually made of quarks. I will review some of it in a little bit. Those elementary particles, the building blocks of particle physics, are then the true atoms as we understand them, the true elementary stuff. And they satisfy equation like the one below here, this is like the Dirac equation that govern the motion of an electron in the vacuum. Now, these rules of quantum mechanics are a bit unintuitive, and many of you will not have studied it just yet. But in the end, it's essentially linear algebra, and you've all seen probably linear algebra already, like matrices and vectors and how to diagonalize a matrix. And quantum mechanics essentially tells you that a lot of what we call physical observables are just big matrices that you need to diagonalize. For instance, this equation will be when you have some particular quantum mechanical states denoted by psi, and you want to know what is this energy. And you need to do that, you need to diagonalize a big Hamiltonian operator, which is essentially an infinite dimensional matrix. Okay, so that's what we will call non-relativistic quantum mechanics these days. Then there is the extra level of subtleties that particles are actually relativistic. So they satisfy this symmetry of special relativity that was discovered by Einstein in 1905. I will describe this a little bit more in a couple of slides. But the fact that the relativistics make the whole mathematical description of particle physics a little bit more shaky. I just said that quantum mechanics was essentially linear algebra, and this is literally, I mean, there is a precise sense in which you can deal with infinite matrices and so on. This is very well established mathematically. There is no problem with that. We can explain that to our mathematical friends as physicists. The situation with relativistic particles in particle physics is a bit more shaky. It works, we know the rules of the game, we know how to compute, but on the other hand, I still have a completely hard time, or it's almost impossible to really explain to our mathematical friends what it means, because essentially we don't have like all the axioms and the very rigorous framework, probably because we don't understand what we're doing as precisely as it would be needed for a fundamental understanding of it. Nonetheless, we have this rough picture, I mean, this very precise picture, but rough mathematically, of the world as a bunch of particles. There are electrons and so on for the matter, and then there are also particles which are really the force carriers. So whenever there is a force, like attraction of two electrons by electromagnetism, I mean repulsion of two electrons or attraction of an electron and a proton, then there must be those particles that exchange the force, and those particles are the photon in this case. And we have all kind of process in particle physics that we represent by those little diagrams, which are called Feynman diagrams, when here it would represent, for instance, an electron that emits another particle, and then this particle is absorbed again, and this kind of thing mediate forces or various interactions. So those are the kind of picture of the world we have very roughly today. And you might ask, are there more elementary objects, right? We know that we thought for a little bit of time, for a brief period of time in history, we thought atoms, we found the atom, and then soon people discovered the atom is really made of electrons and protons and neutrons, and themselves, they are made of quarks. And you might ask whether there is something more elementary. For instance, string theory proposed such a picture, but we don't really know that it really holds experimentally for various reasons. I think you just had a lecture about string theory last week. So as far as we know, those elementary particles are the ultimate atom, as far as we know so far, the atom in the physical sense. Now, interestingly, quantum field theory, for various reasons, is a very broad and rich concept. So it is applied to describe elementary particles like the electron and the photon and so on. But it's also applied in many branches of physics for describing other type of phenomena, which are not like fundamental in the sense that there will be, some description, for instance, of water. You can describe as some wave equation and so on. You describe water with some things that has nothing to do with the fact that it's made of molecules. You just describe some effective motion of the waves. And in many cases, this kind of wave motions in a quantum world, which is our world, you can describe by some what is called effective quantum field theory. And the rules of this are the same as for elementary particles. So really, I can say with confidence that the most important branch of physics today, or the most versatile language of physics, is quantum field theory. And those quantum fields come in many kind of flavor and colors and so on, but they're all fields. And then once you specify the kind of fields you're dealing with, you can play the game of quantum field theory and try to extract prediction for experiment. So do you still see the slides, right? Here we have, yeah. So QFT then is one of the greatest intellectual achievements of humankind. I can say that like qualitatively, there are many quantities that we can predict from theory, and then you check in particle accelerators, and it matches to astonishing precision. So a very famous example is the so-called anomalous moment of the electron. So it's a quantity that without all the subtle corrections from quantum field theory would be equal to 2 in some units. And then you look at the corrections that have to do with this kind of diagram that I wrote here, that you have an electron that interacts with itself, or it interacts with a photon. And all this kind of interaction will correct this result. But you see it corrects with a tiny amount in this case by 1,000th, and then you have all these numbers that you can really compute and match to experiments. In fact, Julian Schwinger here, that's his tombstone on the right. He was so proud when he first computed at least the first 2 digits here of the correction that he put that on his tombstone, the alpha coefficient. So despite these beautiful successes, many aspects of QFT remain poorly understood, and one of the conceptual reasons for that is relatively simple to explain. It has to do with the strong coupling problem. This is the issue that in many cases, like in this particular problem, I have this number about to compute the correction to G equal 2. And I compute and I see that the first correction, correction, I mean that quantum correction. There is something which you might call a classical physics approximation, and then you have quantum corrections. And in many cases, those quantum corrections are tiny numbers, like here 0.01, right? 0.001 of the original result. And then you can organize the correction in this kind of series. When you have alpha is a tiny number, alpha over pi is a tiny number, and then with a coefficient C2, and then alpha over pi squared is an even smaller number. So we have this what we call small coupling, and then you just need to compute order by order in this what we call a perturbation theory of series. So there is a series of coefficients, all smaller than the previous one, and you just sum all of these corrections. So when you do that, then you're on good shape because you know what you're doing. You know that you can neglect the next correction, but it will only appear at the 5th digit or the 7th digit, so you know what you're doing. But what if what if it could happen, and it does happen in some theories, that in principle this correction, these alpha parameters, would be or will be 1 instead of 1%. It will be 10% or 50%. And then you will have like 2 plus 1 equals 3 plus 1. Then you don't know what you're doing. It could be whatever. And in principle, you still have to sum all this correction, but you don't really know how to make a sense of this computation precisely. So this is what is called the strong copy problem. I have this metaphor of a field here. If this is a class, this is what we call a perturbative field, it's something with only small corrections. That's a very nice picture of a sunny sky. But this is my strong coupling problem, when all the interaction or the self-interaction of the field with itself is so strong that it becomes very messy and we don't really know what we're doing. So for this and other reasons, but mostly for this reason, I think 1 century after its inception, quantum field theory was first described, at least for electron and photon, in the 1920s. But 1 century later, we are still trying to understand what QFT, quantum field theory, is all about. It's still very much a work in progress, and we're still developing new tools to do computation in quantum field theories in an efficient way. So quantum field now, I'm telling you about quantum field, but maybe I should tell you a little bit more about what they are. Well, I guess I won't tell you too much about what is a quantum field. Our current understanding of physics is organized around a few principles, which all point to quantum field theory. And those principles are symmetries, and I will focus a lot in this talk about symmetries since we want to talk about supersymmetry. Then there are other principles which are very important. There is causality and locality, which are related to some symmetries, as we'll see, but this is like the key insight of Einstein's theory in 1905, special relativity, and that I will discuss a bit less today. And then there is a very general principle of quantum mechanics. Essentially, these things that I was telling you, that quantum mechanics, in some broad sense, is just the statement that observables satisfy some kind of linear algebra. Observables means anything that I can actually measure in experiments. And using only those 3 principles, one can derive the general structure of quantum field theory, the general rules in which quantum fields interact, and we can write rules for computing things like this correction here and so on. So let me first focus on the first principle. Of course, symmetry is a very important concept in physics from day one. Symmetry is just an invariance of some physical description. So for instance, we might have some problem with some potential or something like that in classical mechanics, which has rotational invariance, like on this picture on the left. And then we will use the right coordinates, for instance, radial coordinates, to take advantage of the rotational invariance. So in that sense, they are just something that we use to simplify a problem in physics. And there is this classic joke about the spherical cow, that if a physicist try to model a cow, it will first assume that the cow is spherical because it's simpler, and then you will try to see if the legs and the head are small corrections. Well, in that case, they might not be, but that's the same problem. Mathematically, symmetries are described by groups and the representation theory of a group. So I don't know how much you might have seen about groups formally in mathematics yet, but roughly speaking, they're just a bunch of transformation laws and how to combine them, right? So if I have, in particular, one of the definition of a group, if I have 2 elements of a group, G1 and G2, I can multiply them and get a 3rd element of a group. For instance, if I have rotation in 3 dimensions, I can go rotate along one axis, rotate along the other axis is the same as doing a rotation along the 3rd axis. So in general, we can just use symmetry to try to simplify, and maybe the symmetry is not an exact symmetry of the problem, it's just an approximation and so on and so forth. And it's a game we try to play from the start, and it's an important part of becoming a physicist is to try to rely on which approximation is accurate to try to get an hang of a problem. Because in general, we cannot solve physical problem explicitly or exactly, but we try to have an approximate solution first. But there are also what we will call fundamental symmetries of nature, because those, as far as we know, are exact symmetries. And one of them is translation, so meaning that if there is empty space, we can go in translation along time or along space, and the physics looks the same. Then there is also rotation in space and rotation in space-time, which is Lorentz invariance, which is the last part. Lorentz invariance is the part which was discovered by Einstein. And that is what is related to causality. Here I drew the light cone of an event, of a person. So light cone means that, so vertically there is time and horizontally there is space. And light can only go along the light cone because it goes at fixed velocity, the velocity of light. And then any information can only go less fast than light. So it has to go inside the cone towards the future, towards up in my picture. So this is what we call space-time symmetries, or sometimes a Poincaré group. So rotation, Lorentz invariance, translation. There are also a few more subtle symmetries of particle physics, as we know it, which are called internal symmetries. They are essentially symmetries that mix particles with each other. Now, any symmetry is associated with a conservation law. This is the content of Noether's theorem, discovered in classical mechanics as a mathematical statement, in fact, by Emmy Noether in the early 20th century. But Noether's theorems also are old in particle physics in quantum field theory. For instance, it says that if you have time translation symmetry in any physical system, then you have conservation of energy. And it's essentially if and only if. Similarly, space translation symmetry is equivalent to the conservation of momentum, of the total momentum of a system. And for internal symmetries, there are similar conservation laws. For instance, there is a kind of U1 symmetry that means something that essentially rotates the electron into itself, or the electron field. And this is equivalent to the conservation of the electric charge in the universe. Now, to proceed with my discussion of symmetries, I need to introduce a couple more concepts about particle physics, which has to do with those symmetries, which is that particles, a given particle like the electron, will come with just a small list of what we call quantum numbers, which are key properties of the particle, which are relativistic invariant. That means they are invariant under all this Lorentz transformation and translation and rotation. One of them is the mass of the particle. And the other is a spin. The spin is some intrinsic angular momentum, as the word spin suggests. So but it's intrinsic to a particular particle, and it's just an half integer in unit of h bar, the quantum of action in quantum theory. So in particular, the electron has spin 1/2, is a spin 1/2 particle. Here I show a picture in blue here of what used to be called bubble chambers in particle accelerators in a couple of generations ago already, where you have like something like an electron or other particle that moves very fast in a bubble of water and leaves a trace. And because of its spin, essentially, when you put a magnetic field, it starts spinning and doing those beautiful lines. And by looking at those lines, that these techniques like was already invented 1 century ago, then you can determine things like the spin and properties of the particle and its mass. The second and I think last bit of fact about quantum field theory I want to emphasize is the fact that there are two types of elementary particles, or any type of particles in relativistic quantum field theory, the bosons and the fermions. And the exact definition is a bit subtle. It has to do with quantum mechanics and the way when you act with a field, because any field is also a particle, and when you act with a field on the space of all states in quantum mechanics, you can act with one field and another one, so to speak, B1 and B2, or the other one, B2 and B1, right? And you can do in one order or the other. Classically, we would say they commute if you get the same result. In quantum mechanics, they will almost commute, but they do not. The commutator, this object here, will be given by h bar. And this is for what we call a boson. A fermion is a field that behaves almost the same way, but with a plus sign. So if you classically, so h bar, when h bar equals 0, if you act with a field and another one, or the other one and the first one, then you get the same result with a minus sign. So this is what is also known as a statistic of the field, and it has to do with how you quantize these fields in quantum mechanics. And a deep fact that I want that is really a theorem of quantum field theory is that all bosons have integer spin, like spin 0, 1, or 2, and the fermions have half integer spin, spin 1/2, essentially, in all the case we care about. Okay, and then finally, in actual nature, in experiments, we observe that matter fields are described by fermions. So that's, we don't know why is the case really, but we just observe that all what we call matter that makes the stuff we are made of are fermions. The electron is a fermion, the quarks inside the atom are fermions. On the other hand, the force fields, like the photons that carry the interactions between matter particles, are bosons. So there is all here in red in this picture, there is the photon, and there are gluons and other particles, elementary particles for other forces. And then there is one spin, so those are spin 1, and there is one spin 0 particle, the Higgs boson, which was famously discovered, 8 years ago. Yes. Now we just saw, I just said that the symmetry group of any QFT is those spacetime symmetry times some internal symmetries. And by definition, those internal symmetries, we say commute with the spacetime symmetry. That means that, again, if I act with an internal symmetry and then with a translation, for instance, or I first act with a translation and then with the internal symmetry, I will get the same result. This seems natural, but it's not guaranteed mathematically. I mean, in mathematics, we could easily imagine that all these transformations are part of a larger group, which like talk to each other in a non-trivial way. Here, I draw a picture of such a group embedding. Here, if you see this sphere, the sphere is to represent rotation in 3 dimensions, because I can go along any direction on the sphere, like vertically or horizontally. That will be a particular rotation group that we call SO3. But if I just go along the equator, this is just going along a circle. It's a one-dimensional group. But this one-dimensional group is embedded in this higher dimensional group of rotation. And you might ask, what is the most general group that can be satisfied, that by which we transform particles or fields, quantum fields, into each other in particle physics? So it's a question that people asked in the 60s when they were confused by many crazy experiments, when they were finding thousands of new, almost thousands of new particles, and they were trying to organize them. And of course, when we have many confusing results, the best thing is to see if there is not a symmetry that would organize this result in a nicer. For instance, if you have n particles, but you see it's a vector that transforms in a given way under a rotation group, like some matrices and so on, then you're in better shape. Even though it looks like a very long vector, you understand it as just not n different numbers, but a single vector. So the same with particle physics. We would like to understand what is the more general organizing principle, symmetry principle for particle physics. But lo and behold, in 67, Coleman and Mandula, here is Coleman here on the right, they proved that in any reasonable particle physics experiment, the symmetries that will be apparent will only be the symmetries we just discussed. So ISO 1,3 is the mathematical way of saying this space-time symmetry group of Einstein, and G is the internal symmetry, G internal. Now, this is a theorem as far as physics theorems go, but any theorem is only as good as its assumptions. And here, what they assumed implicitly was that all the symmetries are bosonic. What it means is that it's a symmetry that always sends a boson to a boson. It sends an electron to an electron and a quark to a quark. Maybe it can send a quark to an electron, but it cannot send a quark because those are the electron and the quarks are both fermions. So it sends boson to boson, fermion to fermion. So it can send, for instance, maybe a quark to an electron, but it would not send a quark to a photon, because while the quark is a fermion, the photon is a boson, as we saw. So this assumption that the symmetry is bosonic, so it sends boson to boson, fermion to fermion, it's actually not necessary, and that's where supersymmetry comes in as an idea, as a mathematical idea at the beginning. It was discovered, in fact, a few years after this theorem by Coleman and Mandula in '67. So the actual story is a little bit confusing, and because it was discovered by various people in '71, both in the United States and in Russia. And at the time, they didn't really talk to each other, so they didn't really know about each other for a little bit. So anyway, by the mid-'70s, it was well understood by various groups that you had such a thing as supersymmetry, and that it could be realized theoretically in quantum field theory. So what is a supersymmetry? It is a symmetry, as you might expect, generalizing this picture here at the bottom, right? Supersymmetry, that I will denote by Q in the rest, or curly Q, is any symmetry, by definition here, that can send a boson to a fermion or a fermion to a boson. So this seems a bit strange and very interesting, because we just saw that bosons are all the particles of forces and fermions are all the particles of matter. So supersymmetry is really mixing, in some real sense, exchanging particles of forces with particles of matter and vice versa. So this is the idea of supersymmetry, and the Coleman-Mandula theorem can be generalized to this case. The space-time symmetry in this case is enlarged, but in a very limited way compared to this result of Coleman-Mandula. So what will happen is that the space-time symmetry will be part of a slightly larger group, which is called the supersymmetry group, or technically the supersymmetry algebra in this case. It goes as follows. So you have a new, okay, let me explain this notation here of the three commutators in the middle of the slide. So the first P commutator with Q equals 0 means that you can do a translation, do a supersymmetry, or vice versa, you get the same result, right? The second one tells you that if you do a rotation, then do a supersymmetry, or instead do a supersymmetry, then a rotation, you will get a supersymmetry. This is related to the fact that the supersymmetry itself will have a spin, and spin is just a type of rotation. So J here is the angular momentum operator. And on the other hand, if you do a supersymmetry and a supersymmetry, or minus a supersymmetry and a supersymmetry in the opposite order, what you get is, I mean, if you do a supersymmetry and a supersymmetry, then plus the other supersymmetry and a supersymmetry, technically, what you will get is a translation. So in other words, you can act with supersymmetry twice and you get a translation. So as you can imagine from the first line, right? I told you that Q acting with Q sends a boson to a fermion. Then I can act again with Q, then I send the same fermion back to a boson. So it goes back to itself, so to speak. Well, it gets back to itself up to a translation. It's what the last equation says. It will get the same boson you started with. If you act with Q twice, it will send a boson to the same boson translated. So in that weird sense, supersymmetry, you can say it's really a space-time symmetry of a new kind, which is, as you can see, morally speaking, from this last equation in the middle, it's a square root of a translation. I mean, it's a slightly imprecise way of saying it, but maybe it's a more striking way of seeing that the supersymmetry is just a slightly more subtle type of space-time symmetry that we didn't discover until the mid-20th century. Like Galileo already knew about translation. He had all this beautiful picture about how balls balls that you throw away in a moving ship will fall at the same rate, at the same place as if you threw it out if you're not on the ship and so on. This kind of thing, this game that we do with trains now in first year physics. So this kind of thing were not intuitive, but they were well understood by a few centuries ago. And then Einstein in 1905 understood all the symmetry of space-time, which are bosonic. But then and those are realized in nature. But then thinking about it just essentially mathematically, like first principle, we came up with a notion. I mean, people in the mid-'70s that I quote in the bottom here, especially Wes and Zumino at CERN in the mid-'70s, understood very precisely that there was a new type of space-time symmetry called supersymmetry, which is this kind of weird square root of rotation that mixes bosons and fermions. Now, this was a theoretical discovery. And then, of course, being physicists, the people who discovered that, and not mathematicians, they thought, oh, this is so beautiful idea and so on. It must be realized in nature. We will just try to find how this is realized in particle physics. And we've been looking for a while, for a couple of generations now. And we were pretty hopeful that we would discover supersymmetry in particle physics, maybe in the 90s, and then at LHC at CERN in the last experiments over the last few years. But so far, no luck. It has not been observed. So there is a good reason why it's not obvious that it should be observed, of course. Our world, as we see it, we already knew from the start that it's not supersymmetric. Sadly, maybe sadly, I mean, although thankfully for us, because chemistry would be very different if we had supersymmetric particles. But it is clear that our world is not exactly supersymmetric because of essentially this supersymmetry algebra I showed you here. You see, the first equation is telling you that momentum and supersymmetry commute, but momentum in relativity is essentially the same as the energy of the particle. I mean, it's related to the energy, the momentum squared, or what I call the mass here. The mass is really the intrinsic energy of the particle. And if supersymmetry commutes with momentum, then it means it commutes with the energy or the mass of the particle. And so if you act with a boson of a fixed mass here and a fixed spin, the supersymmetry sends you to a fermions of the same mass. And so the spin shift by 1/2, right? So if you have a fermion spin 1/2, you can go to spin 0 or spin 1. And if you start with S equals 0, spin 0, you can get to a fermion of spin 1/2. But the mass stays the same. So if supersymmetry is an exact symmetry of nature, each time we have an electron, which has a fixed mass that we know experimentally to be this tiny number, right, 9.1 10 to the minus 33 kilograms, then there should be such a thing as a selectron, which would be a particle which has spin 0 and the same mass. And it should also have the same electric charge as the electron. But if there was such a light particle with electric charge 1 like the electron, we would have discovered already. I mean, our world will be completely different. So clearly, there is no such thing as exact supersymmetry in nature. But of course, people knew that from the start. But the idea was that maybe our world is not supersymmetric in everyday life, but it's completely imaginable, and it can be more precise, that the world is supersymmetric at a more fundamental level. So if we go very, very small distances, which means very, very large energy, or in terms of the history of the universe, very early, very soon after the Big Bang, when the universe was very hot and dense, maybe the world was supersymmetric. And then what happens is that there is something that we would call a phase transition, like when a liquid becomes a solid, right? Like when water becomes ice. So supersymmetry then would be the symmetry of water, but then when the universe becomes like dark and boring like today, the symmetry freezes out, and you're left with a non-supersymmetric world. This kind of phase transition scenario is called spontaneously broken supersymmetry. And this can happen in various theoretical scenarios. The catch is that the energy for this phase transition might be very high. It might be just a tiny moment after the Big Bang. And then it's very hard to recreate the condition for supersymmetry in particle accelerators. So we were hoping that if supersymmetry, this breaking of supersymmetry is relatively, it will be very high energy, but it could be low enough that we can actually reproduce this energy at CERN or at SLAC or other particle accelerators around the world. And so people were hoping to observe supersymmetric partners when you go to higher and higher energy in particle physics experiments. But as I said, we had no such luck. We had some reason that were never completely airtight to hope or like be well motivated, thinking that we would find supersymmetry, but maybe those reasons were not that good. And they were not like mathematical deep reason. There was always a bit of philosophy to it. And so we were not so lucky. Nonetheless, of course, supersymmetry, I mean, theorists will not let the experiments, I mean, we know only recently that experiments do not favor supersymmetry. But back then in the 70s, people thought, okay, maybe we'll find it in 10 years. And then so far we waited almost 50 years. But in any case, theorists don't really wait for the experiments to do their work. They just work on whatever they find interesting and fruitful to do new type of computation and so on. And so why once supersymmetry was theoretically discovered, I realized that I will go a little bit way over time. Well, you tell me when I should stop. Supersymmetry then was studied intensively in the last few decades, and one of the important use of supersymmetry that I want to emphasize today is that independently of whether supersymmetry is realized in the world, in particle physics, in nature, it's very interesting theoretically to tackle problems, conceptual problems that we have with quantum field theory, like these strong coupling problems I was telling you earlier. And I will conclude with, at the end of the talk, I want to discuss a little bit how we use supersymmetry. I mean, collectively humanity, and in particular Seber and Winter in '94, use supersymmetry to solve a particular type of quantum field theory, which is strongly coupled, but they use supersymmetry to solve this. And without supersymmetry, we would never be able to do this kind of huge computation. There was also the last 2 points about particle physics and cosmology is that at least up to relatively recently, over the last up to 10 years ago, there was good reason to think that supersymmetry would give solution to various puzzles in cosmology and particle physics. But I think so far, those ideas have not been successful experimentally. So that's why, as a theorist, a physicist who lives in the mathematical physics building, I really think of supersymmetry as a theoretical tool. And that's what I would like to emphasize in the remaining of the talk. So this was the history of particle physics and how supersymmetry arises and what it is in particle physics, or in broad terms in physics. So if there are any questions about that, before I go into a slightly more mathematical part of the talk. Okay. Question? Yes. Yes.
So you said that a symmetry implies a conservation law by Noether's theorem.
Yes.
So what is conserved in supersymmetry?
Very good. So, I mean, there is a conservation. There is a Noether theorem for supersymmetry. It's called a supercharge, and yeah, so the thing is, it's not something that you would know of because, well, first of all, we don't have supersymmetry in our world. But yeah, there is mathematically an object, which is the supercharge. And in fact, the supercharge is what I call Q. Because what is a charge? A charge is essentially an element that will generate a transformation in the group. And this charge is conserved. Like the electric charge is what generates this kind of internal symmetry of the electron. And here Q is what we call the supercharge, and that's what is conserved. So meaning that this is a part. Q will be essentially concretely some kind of complicated function that you build out of fermions and bosons in a QFT. And this particular combination of boson and fermion in a supersymmetric theory will be time invariant, so it will be conserved. That's the supercharge. Yeah.
So is it like it is not a particular property of one particle, but like some complicated function of?
Well, no, I mean, it is a general property of the, okay, it is a general property of the system, a supercharge. But in the same way, the translation invariance is a general property of the system. And then you can, in quantum mechanics, you can always realize those charges as some kind of operator that is built out of the particle in your system. And you always have particle acting on particle, but it's a particular, yeah. But anyway, it is just a particular property of the system. It's just that because it's a fermionic charge, it's not something you heard that like conservation of energy. There is a conservation of supersymmetry in that same sense, except that it's less intuitive. I mean, it's not something we see in the real world. So, but yeah, they will be nonetheless. Noether theorem is still true, and so there is a conserved supercharge. Okay. Any other question? All right. So let me then go through slightly the less technical, the more technical part. I thought, you know, when you do this kind of when you hear this kind of talk, I mean, I remember reading about string theory in books and so on when I was in first year or in high school. And there is this thing when you can only do so much, right, without equation. And then when people write like physics book, the editors will always tell them that you use half of your readers each time you write an equation. I think the only person who solved books with equation in it is Hawking. And I'm not Hawking, but we are also among, Oxford students. So I will take the risk here of assuming that you would like to see a little bit more under the hood of what is going on with supersymmetry. So I will show a sort of toy model of supersymmetry when you can see how this supersymmetry helps solving problems using a model of supersymmetry in just ordinary calculus. Okay, so let me then, sorry, where is this? Yes, so you see here this particular curve, this integral, so the volume under the area under this curve, this integral e to the minus alpha over 2 x squared, an exponential of x squared, that you've probably seen that in some calculus exercise, or to solve this. If you do the integral from minus infinity to infinity, so the whole volume under the Gaussian is square root of 2 pi over alpha if I introduce this coefficient alpha here in my function, right? So this is one integral we can solve, and of course there are a bunch of small integral we can solve like this, but if I give you a more generic integral, like an integral here at the bottom, dx of g of x e to the minus half fx squared. So why do I write it like this? Is because I could have an arbitrary function g of x multiplied by an exponential of minus f squared. So f squared, if x is real, so f of x is a real function. So f squared is a positive definite, and so we have something which pretty much looks like a Gaussian in the sense that it's damped very much at infinity. So this integral has a good chance if g is not if g of x, the function g of x, is not growing too fast at infinity. This function has a good chance of being well defined. The integral will have a tiny contribution from infinity, and then you can try to sum all the area under the curve, even though it might be a complicated looking curve, right? So the question here I want to answer is, how can we solve this integral in general? Well, in general, we cannot. I mean, it's just a fact of life. We can compute those integral numerically, but there will not be a closed formula to solve for this. Like I can say that the Gaussian is just a square root of 2 pi. But there are some nice type of integrals where I can actually solve it exactly. And I would like to explain one such integral and give a proof of that using supersymmetry. So here is the integral of the form here, right? I have dx of g of x times exponential of minus 1/2 f to the squared. Now, what if I take f and g to be related to each other? I will take the function f in the exponential to be some function w of x, first derivative of it, the first derivative of w, so w prime x squared in the exponential, and then multiply by the second derivative of w, right? And I want to compute this. So I give one example at the bottom. On the left is the graph of some function w, which is here is a particular quartic function. And then if you plug into the integrand here, w prime prime e to the minus 1/2 w prime squared, that's the one on the right. So it looks like, roughly speaking, a bunch of Gaussian, but really it's much more complicated. It's some peak like that. It's just that it looks like Gaussian because it's very tightly peaked toward around some points. But you want to compute the area. Here you see that we seem to have two positive contribution, one negative contribution, and we know what they want to solve, what they sum to. And good luck to try to do this computation directly. I mean, nowadays some computer program can do it for you probably, but if you do it with pen and paper, I mean, in some cases you can find some clever tricks, but in this case, I think it's pretty hard, and I can give you even more complicated polynomials and so on, or more complicated function. And my claim is that the result will always be a multiple of square root of 2 pi. In fact, in this case, it's square root of 2 pi, and in general, it will be either plus square root of 2 pi is if the function w on the left here goes to infinity, plus infinity on the left and on the right. It will be 0 if it goes on plus infinity on one side and minus infinity on the other side, and it will be minus it will be -1, so minus square root of 2 pi, if the function is like goes to -infinity on both sides, on the left and on the right in x. So that's the statement of that's my statement here, this claim, and I would like to prove this. So how can I prove that? Well, I will introduce some crazy looking things that will not be too surprising now that we discussed fermions. So X, you can think of like the bosons in this game. They're like bosonic fields, spin zero fields. Now, what if I introduce a fermion? A fermion in ordinary calculus will be what we call the Grassmann number. Those are those formal numbers that are denoted by theta, which are generating this, what is called a Grassmann algebra. So theta is a number that's square to 0. It's non-zero itself in some sense. It's an abstract algebraic number, but it's square to 0. And similarly, I will introduce another number which I call theta bar, which in some sense you can think of the complex conjugate, but they're independent. Theta bar square to 0. On the other hand, if I look at the anti-commutator, so t theta bar plus theta bar t, I get 0 again. So it means that they anti-commute. So if I take one or the other and the other one, I get a minus sign, right? So that's by contrast with ordinary numbers which commute, right? I can xy is equal to yx in ordinary commuting numbers, ordinary algebra. So those Grassmann numbers look a bit odd, but they can be treated in many ways very much like ordinary numbers. They just have these weird rules that they square to 0. Then you can also derive and integrate along Grassmann numbers. And in particular, integrating is defined as follows in the line below. So if I integrate d theta over some alpha plus beta theta, that's a generic function of theta, in fact, because I can always expand any function in power series, and it truncates at theta squared because theta squared equals 0. So this is a general function of theta, and it just integrates to beta here. So that just means that the integral of d theta theta is equal to 1 by definition, and everything else is 0. That's my definition of an integral. And in fact, yeah, that's the correct definition. And from this definition, you can see that if I have this object, the exponentiated theta bar, or theta bar theta, sorry. I mean theta bar, exponentiate of a theta bar theta, and I integrate this along d theta and d theta bar, I will get a. That's the last line. What I did here, I have a function which is an exponential. The exponential is defined by its Fourier series. This is the fact that the exponential of x is 1 plus x plus 1/2 x squared, and so on and so forth with an infinite series. I can do that with these Grassmann variables, but it stops at the first term because theta squared equals 0. So I just get the second thing, and so I integrate, I get a. So this is the analog of this Gaussian integral for the x variables. The Gaussian integral is something we can do by standard methods. And the Grassmann integral for Gaussian is even simpler. It's just the coefficient here. Okay. Now, why introduce this beast, this fermionic number, the Grassmann number, is because I want to write this integral w with the integrand being w prime prime times the exponential as a single exponential. Makes it simpler, and it's very natural in physics. So I write the same integral as exponential of -1/2 w prime x squared to the square plus theta bar theta w prime prime. Since we just saw by this last line here that the exponential is the same as just bringing down the coefficient of the theta prime theta term. So this is literally the same, but written in a fancier way, but it's the same as my integral I started with. Okay, so I just write this same line again in the second line in the box as this integral over the x, the thetas, and the theta bar. And I forget the integral is from -infinity to infinity in x, that's implicit here, of e to the -s, when s is a function that in physics we will call the action, which is 1/2 of w prime squared minus theta bar theta w prime prime. Okay, so I'm just rewriting the same thing. Now, the interesting thing is that this action S has a non-trivial supersymmetry. So again, a supersymmetry is something that maps the boson, which is my X, to a fermion, theta. In fact, here one can check, and I encourage you to check if you write it down and check on your own time, that when I act with Q, so the symmetry is defined as follows. There is two supersymmetries, really, Q and Q bar. There are two independent actions of supersymmetries. So Q acts on X and gets theta. If you act again on theta, now you get 0. Okay. If you add with Q on theta bar, the other fermionic variables, you get W prime of X. Okay, so again, a boson went to a fermion goes to a boson in equals 0 in that case, or to a W prime of X, which is also a boson. It's a bosonic variable. And similarly for theta bar, with some minus, there are two different supersymmetries of this action. So this action is supersymmetric. In this definition of supersymmetry, it's just a particular action that you need to determine or guess or whatever that rotates, that mixes bosons and fermions. Now the supercharge Q, so what I mentioned before, the supercharge is conserved quantity, or the thing that generates the symmetry equivalently, the supersymmetry. You can see it as a derivative, the same way that you can see translation as being generated by derivatives on fields. And Q is generated by this particular first order derivative. It's a fermionic operator, so it's theta, which is fermionic, times the derivative along X, the bosonic direction, plus W prime of X times the derivative along theta bar. And taking the derivative along theta bar, it just means collecting all the terms with one theta bar and taking the coefficient, like the integral. Okay. So I just wrote this fancy integral in a supersymmetric way, but what does it buy me? Well, let me first consider a side generalization of the same integral. I will just multiply W by any coefficient lambda. It's a real positive coefficient. Could be equal to 1, you get back the original things, or it could be equal to 100 or 1 million. So you just rescale W by lambda, then the action is that I will now call S of lambda is rescaled like this, right? Because it's W prime squared. So there is lambda squared in the first term, or lambda in the second term. And the supercharge itself depends on lambda in front of W. But I didn't change anything. It's just a change of notation if you want. I just pull out this coefficient lambda, and my action is still supersymmetric. Q lambda acting on the action sigma lambda, S lambda is equal to 0. Now the claim is that this supersymmetric integral is actually independent of this coefficient lambda, the overall coefficient on W. The proof is one line and is the most important proof in supersymmetry. The proof is 4 lines, sorry, here. It goes as follows. So let's see, what does it mean that it's independent? It means that the derivative of I of lambda with respect to lambda is actually 0. So let's do that. Take the derivative of W of I of lambda with lambda. You can easily, it's E of S of lambda. S of lambda is given here on the third line. So, well, you can do the derivative of E of a function. So it brings down the function, take its derivative. So that's the first line. Now, these first lines can be written as Q bar. It might be Q. Anyway, I think it's Q. Q of lambda on theta W prime. So you can check that the thing in parentheses in the integrand, the first line is actually Q, the supercharge, acting on theta times W prime. But we also saw that Q leaves the action invariant. So I can just, in the third line, put everything around the same parentheses, meaning that the supercharge acting on all of this is 0. Sorry, it's not 0. It acts on the first term, it gives the first line. It acts on the second term by the chain rule. It just gives the same because the action is invariant. S is invariant, so I mean Q of S is 0, so E to the minus S stays the same product, right? It factors out. Okay, so last line, I just write out explicitly the supercharge Q of lambda. Sorry, there's a typo. It's Q, not Q bar. And it's just this operator, as we said, is this differential operator. So the first term, it's like an integration by part that you probably have done many times in integrals. So it just tells you that it's a dx of a total derivative of something. So that's the fundamental theorem of calculus or something like that, right? So it just gives you the results of whatever is on the right at minus infinity and plus infinity, the boundary point of the integral. And by assumption, because of the exponential, those vanish. So this gives 0. And the second term, it's an integral over d theta bar. But there is nothing that is of order d theta bar on the right here. So this actually gives 0 as well by the definition of the Grassmann integral. So we just proved that this supersymmetry, this supersymmetric action does not depend on the coefficient lambda in front of W, this function W. Okay, so finally, I can take then a limit to compute it more easily, since I just told you it's independent of lambda. So what we will have to compute is when lambda equals 1, but then I can just take a limit when lambda goes to infinity. And you have to be careful that nothing drastic happens when you take this limit. But under some mild assumption, nothing will happen if you just continuously move it all the way to infinity. But if that means I will weight my integrand by this factor, e to the minus lambda squared, when lambda squared is very, very large. So what happens in this limit? Well, I can try to take the limit of this function, e to the minus lambda squared of w prime of x squared. And obviously, if w prime itself is non-vanishing, this vanishes because everything is positive definite. So it's e to the minus lambda squared. It goes to 0 when lambda squared goes to infinity. So this seems to naively, of course, tells you everything vanishes, I equals 0. That's not true, because of course what happens is that we still have contribution at the point where this limit is more subtle, because w prime vanishes. And by definition, w prime equals 0 are the critical point of the function w. Now, near each critical point, I can now approximate by a Gaussian integral, because w can be expanded around a critical point by definition. The value of w at this critical point, the first derivative vanish at this point by definition of a critical point, and then the second order term, there should be a 1/2 of x minus x star, where x star is a critical point squared, and the second derivative at this value, right? So it's just a Taylor series expansion to second order. And I can always do this approximation of an integral. It's called the steepest descent method, or some name like that. But the point is that here, when lambda becomes very large, this approximation becomes exact. Each time the integral becomes highly peaks around various points, the critical point, which are essentially those 3 points here on the right, which are the critical point in this example, right? On the left, I have 3 critical points each time when the function w turns. And these are where we have 3 peaks, and we see that the integrals in this example is already very localized near this point. But if I took lambda to infinity, in fact, it becomes infinitely big around this point and 0 everywhere else. And then it becomes very easy to compute. So then, yeah, a couple of more line of algebra shows you that. So you just need to plug in. I won't go through it line by line, but in this limit, then you just get a sum of Gaussian integral. And we know how to do Gaussian integral. It's just square root of 2 pi for each Gaussian integral with a coefficient which will now be, if you follow the algebra through, it will just be the sign of the second derivative of w. In other words, you get 0 if it's sorry, you get yeah, I mean, yeah, for a generic w, you will just get plus if it's concave and minus if it's convex, or vice versa. And the sum then of the critical point only depends on the total topology of the function, which was my claim at the beginning. So again, in my example, for the first w, then this complicated integral I will just be equal to plus 1 times square root of 2 pi. just because I get +1 from the first critical point, then -1, then +1. So that gets +1 in total. And in general, you can easily convince yourself that if it only depends on, it doesn't matter how many ups and downs there is in a generic polynomial or more general function, it only matters how it goes to infinity, if it goes to +infinity or -infinity. And so that proves the claim. So that was an application of supersymmetry to a easy sounding or problem, maybe slight, I mean, you might be slightly bored at this point, but I think it's a fascinating application of supersymmetry. Now, why I go through this is because actually this, I think, if you wrote it down or if you go through the algebra, you can do it, no problem, understand every step, even with first-year calculus. But this very same kind of principle and this simplification that has to do with the fact that my action, what I call the action, this ordinary integral, was supersymmetric, also in quantum field theory, where there I have a much more complicated system. But the key relation is that there is a formulation of quantum mechanics and more generally quantum field theory, which was introduced by Feynman, where every observables, everything you want to know about the system and every quantum observables is written as an integral, except that it's not an ordinary integral with like a finite number of variables. It's like, morally speaking, an infinite number of variables, and such an infinity of variables and a continuous infinity that mathematician cannot make any head or tail of it. So it makes no sense mathematically, except in some simple case. In fact, in quantum mechanics, it does make sense, but not in quantum field theory. But as physicists, we can still work with this kind of integral very formally and compute a lot of beautiful results. So this integral is called the path integral, as I said. And now it will be very similar to what we said before. It's just that my x now are the actual bosons of a quantum field system, and the psi are the fermions in a supersymmetric theory. And the funny thing is that in a generic theory without supersymmetry, this action is very hard. Similarly to if I give you an explicit integral and ask me for a primitive, there is no closed form formula. But in the case when this path integral is supersymmetric, we might be able to solve it, like we solve this, and it's a very active area of research even today to do that in quantum field theory. And one finds a lot of beautiful results in it. So maybe to conclude, if I can have 5 more minutes, I would like to explore, I mean, give an application of these ideas in where there was a beautiful interplay between physics and pure mathematics, and where these ideas of simplification of quantum field theory from supersymmetry was very powerful. And this question, you can ask the question first just as a mathematician, which is the question of classifying a smooth manifold. Okay, so that there might be a lot to unpack here, but we can get away with just thinking of a few examples. So a manifold is essentially a smooth space, like a sphere or a donut or torus and so on. And that's in 2 dimensions, you would have the sphere and the torus, like in the picture in the middle. In 1 dimension, there is just the circle. If it's a closed manifold, and in higher dimension, it's more complicated object that we cannot visualize, but you can think of similar things in 3D, 4D, and so on. And the question is, given 2 such space, two smooth manifold, when are they diffeomorphic? Meaning I can continuously deform them in a smooth fashion. So for instance, it's well known that if I take my cow, for instance, in my example, any animal, I can continuously deform it to a sphere. There is a continuous operation that does that. And so you might be given 2 very different looking manifold in some sense, but they might still be the same in disguise. And the question is, when are they the same? That's the question of classification manifold in mathematics. A particular case of this is when is a d-dimensional manifold a sphere. So that's the Poincaré conjecture in the case of in 2D, in 3D, in 4D, Poincaré gave some conjecture about when is a manifold a sphere a century ago. And in 3D, this Poincaré conjecture was proven recently by Perelman. In higher dimension, in dimension larger than 4, this problem is also solved. Interestingly enough, when you go to 5, 6, and any dimension, it becomes somewhat simpler. I'm not an expert, but I hear from mathematicians that this is well understood. But interestingly, d equals 4, which is our dimension of space-time, but here we're talking about spaces, not space-times, but we're talking about 4 dimension of space, which is curved into itself, so it's closed. So when d equals 4, this is a 4 manifold, and this is the hardest problem for mathematicians as well. There is no solution to this problem of classifying manifolds, but there's been some interesting progress made both by physicists and mathematicians. But first by mathematicians, Simon Donaldson in 1982 came with his theory of Donaldson invariant, which assigned some formal polynomials to a given manifold. And those polynomials the definition is rather complicated, but they depend only on some topological properties of the manifold. Topology means like the number of, for instance, the number of handle in my 2D example. That's this kind of topological properties. So basic properties that do not change when you start deforming the manifold and squashing it and whatnot. So he defined those polynomials that you can compute in principle, and then they would distinguish different manifolds among themselves. The problem is that those manifolds that rely on what is known as a classical field theory, or a gauge theory, more precisely, are very hard to compute explicitly. Now, in 1988, Edward Witten, the famous string theorist and quantum field theorist, realized that those Donaldson invariants that were introduced in mathematics can be taught in physics as a path integral, so quantum observables in a supersymmetric quantum field theory. So this thing that Donaldson thought was a classical field theory is really quantum, and it's actually supersymmetric. That's what. So we can rewrite this complicated, complicated but well-defined mathematical type into this path integral at the bottom. So at the time, that seems like a very interesting point, but it didn't give a way of computing those things more concretely for mathematicians. But a few years later, in '94, Seberg, together with Witten, actually solved this quantum system, and they used supersymmetry crucially. And solving that was interesting both for physics and mathematics. For physics, it was very interesting because it's the first time that they solve a strongly coupled quantum field theory exactly. So I told you it was a very hard problem in that case, and in a few other cases like that. Now it's solved. Now those are models which are not interesting in experiments for nature, but as a theoretical question, it's still very interesting. We have this kind of toy model that we know exactly how to solve, thanks to supersymmetry. And the same year, Witten, realized that this physics solution of this quantum field theory with supersymmetry could be used to write those Donaldson invariants for manifold in a completely new way that was not anticipated at all by mathematicians, but that was very quickly followed up by mathematicians and are now called Seber-Witten invariants. And those Seber-Witten invariants are much simpler to compute and have led to a lot of progress in the theory of four manifold, even though it is still an active area of research that has not been completely solved. So this is, I think, a very exciting example that some of us still work on today, where those physics-based concept and conjecture really help solve very deep mathematical problems. And so 25 years later, we are still working on these kind of things. And that's my conclusion, that supersymmetry is a very, very natural idea in theoretical physics because it's this most general, in some very precise sense, is the most general possible symmetry of space-time that is possible in particle physics, in any world of particle physics. That does not mean that this beautiful idea is realized by nature. Nature has not been so kind so far. Maybe nature is not supersymmetric in any way, shape, or form. It is just a beautiful idea, but it is nonetheless a very fruitful idea, as I just explained in this example, and also in many other examples, especially in string theory. It has been very useful to use supersymmetry as a tool to try to decipher in physics, to try to decipher quantum field theory better, because there are still conceptual question with quantum field theory that supersymmetry helps us address. And perhaps more surprisingly and amazingly, it has been very good at discovering new things about mathematics by just combining insight from physics with this simple idea of supersymmetry. So that concludes this talk, and if you have any question, I'll be very happy to discuss further. And sorry for going over time.
Thank you very much. Thank you for all of details. That's probably that's a lot of information to digest, to be honest. Right. Is there any question from the audiences?
So while people think of their questions, feel free to put them in the chat as well if you're not happy to speak, but do feel free to unmute yourself. Until then, something that we always like to ask our speakers is kind of if someone listening finds this stuff really interesting, and I definitely do. What would you recommend they do apart from going on and picking QFT when they have the chance as one of their lecturers? Should they look at any specific maths? Are there books to recommend or anything like that?
That's a good. Yeah, I mean, there are like various lectures, but like which online about supersymmetry that are very good, but that are like indeed more for master level QFT and so on. And you know, I'm not sure whether there are. I mean, there are discussions of supersymmetry in various like books, of course, about string theory and so on, which are more popular level books. I don't know if there is a good entry about supersymmetry directly in mathematics. I mean, there are advanced books, but not. I'm not sure if I. But let me actually put a pin on that, and I'll try to see if I can send you by email reference.
That'd be great. We'll put that in the event description and the YouTube channel and the YouTube video in the description so people can find it later on. That'd be interesting because that's always it's often astoundingly hard to find good textbooks on something, and then the people who are who know the stuff, they either don't remember which resources they actually use, or they just think it's so obvious that that's the textbook you use. So it's always an interesting question to ask. So that'd be great if you send that our way.
Okay, I'll try to think of a good reference. Yes, thanks.
Right. And so I see that there are questions on the chat right now. The first question by Jeremy is that how does supersymmetry relate to gravity? Oh.
Sorry, I stopped sharing by mistake. How does it relate with gravity? Oh yes, good question. So that's a, maybe let me try to share again. So it relates in a very direct way, but very deep way. In fact, historically, if you look at, probably mentioned it, yeah, when it was discovered, supersymmetry as this concept of in quantum field theory was actually discovered not in what we will call four-dimensional QFT of particle physics, but in string theory. In 1971, the very first model with supersymmetry was discovered by and Schwarz in string theory. And in string theory, it is a necessary condition to have a consistent string. And string theory is the only consistent theory of quantum gravity that we know. So in that sense, the only theory we know where gravity is a quantum theory also has supersymmetry built in naturally. Now this is supersymmetry on a string. So I think you've heard about strings last week. So strings are those tiny little objects, right, that replace particles at the fundamental level, conjecturally. And supersymmetry is a symmetry on the string itself. It's not a symmetry in that theory. It doesn't need to be a symmetry of our space-time in which we live. It's a symmetry that kind of lives on the strings. But yeah, it's in that sense, it's very tied to the idea of, I mean, to gravity as envisioned by string theory, because we really need supersymmetry as a concept to even make sense of the equation of string theory, really.
Right. Thank you very much. And so I see that there's a second question. Oh, there's a third one. Okay. The second question by Xavier, sorry if I pronounced the name wrong, asked, can you tell us about supersymmetry and condensed matter?
I wish I could. I mean, there's been, so I told you that quantum field, right, come in all kind of flavors, and precisely in condensed matter, there are all kind of quantum fields that are effective description of various systems like metals and so on. And we can build, unlike in particle physics, when the number of fields are fixed once and for all, in condensed matter, you can engineer all kind of quantum field theory. I mean, essentially, you have complicated materials, and they can describe by effectively described by complicated quantum field theories with various building blocks. And so you could try to engineer some system in the lab which has both fermions and bosons that will be exactly supersymmetric. I think there's been tried. I think there's been even some claim recently. At least theoretically, it's possible. And so it's possible that it will be, or maybe it has already been tried to build supersymmetric model in the lab, when you would have some kind of metals with bosonic and fermionic excitation that would have this symmetry between boson and fermion. So that might happen in some complicated metal or other type of condensed matter system.
Right. So the next question is that I gave up reading the names right now. Sorry about that. So is there supersymmetry in brains?
Yeah, I mean, so brains are those objects in string theory, right? I guess is what you mean. So like strings is a one-dimensional object that moves in space-time, and brains are higher dimensional membranes that are supposed to move in space-time and that appear naturally in string theory. And I mean, a lot of these objects can be supersymmetric or not, but the one we understand best are all supersymmetric in string theory. And so, yeah, the point is that here I discuss supersymmetry in a four-dimensional particle physics world. If you have three space-time dimension and one dimension of time, but really you can do the same game in abstractly, and we do the same game in any type of space-time dimensions. Space-time dimension 2 is a string, then you can do that in dimension 3, 4, 5, 6, and those will be essentially brain systems with supersymmetry. So theoretically, yes, there is no problem with that.
Right. Thank you. So one of the audiences said that there's a pretty good, I think he means a textbook or something like that. So
yeah, that's a good. I mean, I think it's a pretty technical textbook, but it is a good textbook, which has, as the name suggests, is very thorough. It's very long, but it's available for free online, so you can just Google it indeed. But it's pretty. I mean, I think it's. I mean, I don't know what you're looking for in terms of. I think that's a bit advanced for maybe for undergrads, but yeah, I think it's a good textbook.
Okay, thank you for sharing. So, is there any more questions from the audiences? There's another one. What does Q equal to square root of translation means actually in physics?
Right. Well, in physics, what do you mean in physics? Well, what it means is, I mean, this was more like a square root of translation is not the actual things, right? Because what it meant, the actual relation was Q squared equal translation. Then you can rewrite it in that way formally. So Q squared equal translation just means that, as I said, if you act with one supersymmetry on a boson, you get a fermion. If you act again on the fermion, on that same fermion, you get back the same boson essentially, but translated. That's what Q squared equal translation means. So that's it. Then I mean, it's not been realized in nature, right? So we don't have intuition about that like we have for concept like conservation of energy and so on when we have an intuitive concept. But yeah, it's a similar conservation law nonetheless.
Right. Okay. Is there any more questions? So, right. If not so, I would say that this would be the end of this wonderful extracurricular class. And again, thank you very much for giving us the opportunity. So again, this will be recorded. We will upload this on YouTube afterward, and be sure to like follow the Facebook and all the stuff like that. There's one more question. So I would say that I would call this to be the last question because we're running a little bit over time. Could Q-deformed supersymmetry be used for deriving mathematical facts? For example, smooth manifolds?
Yeah, I mean, I'm not sure what you mean by Q-deformed, but yeah, there are all kind of course, there are all kind of variation on the kind of supersymmetry algebra that you can narrow down the simplest one, but you can deform with various coefficients and so on. And this has been explored in many directions, including to try to, there have been recent work, for instance, by Gukov and his work, a professor in Caltech, who has been trying to use like this kind of more complicated supersymmetric models to try to write more general invariants, generalizing Donaldson-Witten invariants that I talked about. So yeah, you can play a lot of similar games like that with various deformations of supersymmetry. Let's see, there is a last question. How do I perceive it? Well, I can say, I mean, the simplest example is just the electric charge. So it's just the statement that, I mean, I don't perceive it. It's really something that you act on the electron field with a phase, and the Lagrangian is the same. So it's a more technical thing, but it's equivalent to the statement that electric charge in the universe is conserved. Yeah. But yeah, it's a more, those integral symmetries will not be precisely because there's no space-time, there is not this intuition like translation. It's really some operation that you do on the field in the Lagrangian in mechanics or in your quantum field theory, and you see that's invariance of your description.
Okay, I think that will be the end of the Q&A session and would also be the end of the talk. Thank you very much for coming, and also thank Syria for giving us a really good talk. Again,
thank you for having me.
Right. Again, we'll upload this on YouTube. Remember to check our Facebook pages, and I'll see you in the next extracurricular talks. See you. Bye.
Bye.